for real-time applications.
Okay, thank you everyone. Thanks, Balaji. I'm very happy to be here. My name is Haitham. I'm from the University of Illinois, and today I'm going to be talking about sparse Fourier transform algorithms for real-time applications. And so this talk is a bit heavy on signal processing, so I tried to keep it at a very high level. But at the very least, you need to know what a Fourier transform is. And so what a Fourier transform does, it takes a signal in time and computes its frequency representation. So it extracts the frequency components. And it's almost used everywhere. It's used in audio and video processing. It's used in GPS and radar, medical imaging, DNA sequencing, even gas and oil exploration, and many, many more applications. And that's why if we can improve the way we compute the Fourier transform, we can benefit a lot of applications and domains. So how do we compute the Fourier transform? In 1965, Cooley and Tuckey came up with this great algorithm called the fast Fourier transform, the FFT. And for FFT, for a signal of length n samples, it computes the Fourier transform in n log n time. So it's almost nearly linear, and at the time it was a huge improvement. It made a lot of applications practical. But 50 years later, the FFT is no longer fast enough. In some applications like GPS, it consumes too much power. In other applications like medical imaging, just collecting all the samples to compute the FFT means that the patient has to spend a long time in an MRI machine. In other applications like radio astronomy, where they built a square kilometer array in Australia and South Africa, the amount of data that comes in per second, they can't even store it, forget about computing it. So the natural question that comes up is, can we compute the Fourier transform faster than FFT and in sublinear time? And the idea to do this is to leverage sparsity. Let me tell you what we mean by that. It is often that the output of a Fourier transform is very sparse, which means that most of the signals are negligible, and there's only few spikes that have all the energy. And this is exactly the property which is going to leverage to compute the Fourier transform faster than FFT. And at high level, the intuition is very simple. There's no point going and spending time to compute signals that are just negligible or noise. All we have to do is find these peaks and compute their values. And you might wonder, like, how often does this sparsity appear in practice? And actually, all the applications that I just mentioned are actually sparse in frequency domain. GPS, medical imaging, video and audio data, radio astronomy, seismic data, genomics, you name it. And that's why there was a lot of interest since 1992 to work on faster algorithms to compute the Fourier transform. And the best algorithm was basically the fastest runtime was due to Gilbert, Mutakrishnan, and Strauss in 2005. And what they showed is for a signal of length n, if it is k-sparse, what that means is that there's k large coefficients, you can compute these coefficients in k log n to the 4. And this would improve over FFT for any k that's smaller than n over log n cubed. And in 2012, together with Piotr Indyk, Dina Katabi, and Eric Price, we have shown algorithms that can actually compute the Fourier transform for sparse signal. For the exactly k-sparse case, when there's no noise, you can do it in k log n, and you can show that this algorithm is optimal, assuming that FFT is optimal. And when you have noise for the approximately k-sparse case, you can do it in k log n over k, and this is log n factor away from the lower bound. And it would improve over FFT for any k that's small o of n. It's, by motion triggered. Okay, so perhaps what's important about these algorithms is they turned out to be very practical. And we managed to show their impact on the many applications. So we were able to customize them and use them in wireless networks, GPS, medical imaging, computational photography, circuits, biochemistry, and astronomy. Now, since this workshop was on real-time decision making. I'm going to focus on real-time applications, and specifically I'm going to focus on wireless networks. And I'm going to talk about two main applications of Fourier transform. The first is spectrum sensing and acquisition, and the next is millimeter wave 5G networks. So let us start with the first one. Since 2013, for the past 5 years, FCC have been telling us that we have been having a spectrum crisis. All the spectrum has been allocated, and there's no more spectrum to use. And if you're a person who works on wireless or radio frequencies, you'll find that that's surprising. Because if you go and look at the spectrum, you'll find that most of it is unused. So this is a figure from the Microsoft Spectrum Observatory that's measuring the spectrum over a period of 1 day between 1 gigahertz and 6 gigahertz. And as you can see, between 3 and 6, we barely see any signals. So what does that mean? Is FCC wrong?
Who owns that frequency?
Sorry?
Who owns that?
Well, there's many different entities. But the idea is that although the spectrum has been allocated, so FCC have sold it to different parties, it's not being used efficiently. So most of the time, there are many bands in different areas. So this is in Seattle. If you go to another area, this situation might look different. But there are many frequency bands that are not being used. And so the question is, how can we use it more efficiently? And we know the answer. The answer is something called dynamic spectrum access. And what this means is different radios and your cell phones or different devices, what they're going to do is they're going to search for unused frequencies, and then go and use them. But to be able to do that efficiently and in dynamic fashion, what needs to happen is that the radio needs to be able to capture gigahertz of spectrum in real time. So I need to be able to sense what's going on and then find the unused bands and in real time switch there and use it.
There's no legal issue with this, is it? I mean, if you allocate the spectrum to somebody else.
So basically the vision is, this basically came from the White House time of Obama, is that they're going to create these spectrum highways, right? So the FCC has to open it first, right? But basically the motivation is that there's a lot of data that shows it's not being used, and so why not open it for sharing? But if you want to share it, you need to be able to sense it in real time. And it turns out that real-time gigahertz spectrum sensing is actually quite difficult. What you can do today is actually just scan tens of megahertz at a time. So you sense tens of megahertz and then you scan. And the problem with this is that not only it takes time, you can miss fleeting signals and signals that are not always there. So why is it difficult? One of the key challenges is something called high-speed ADCs. And what an ADC is an analog to digital converter. It takes the analog signal, it samples it, and digitizes it. If we were to look at the ADCs that are being used today on cell phones and radios, there are mostly tens of megahertz, so they sample tens of megasample per second. They're very low power. They have high bit resolution, so they give you like 12 to 16 bit per sample, and they're really cheap. But if you want a gigasample per second ADC, it's going to consume way more power. It's going to have way less bit resolution, 4 to 6 at most, and it's going to be quite expensive. And so the question is, can we sense the entire spectrum without sampling at gigasample per second? And the idea is, in the spirit of this talk, to use sparsity. If the spectrum is sparse, we know from sparse recovery theory that you do not need to sample it as fast as at Nyquist rate. So you do not need to sample as twice the highest frequency. And indeed, there's been a lot of work on using compressive sensing to solve this problem. The main issue, however, is that compressive sensing and even our initial sparse Fourier transform algorithm require random sampling. And it's very hard to build a random sampler in hardware. Now, there are ways around it, but turns out that you have to still use multipliers that multiply at gigasample per second that consume a lot of power. And even if you can do that, just recovering the spectrum is computationally very intensive. So what we need to do is we need to have a sparse Fourier transform algorithm that doesn't require complete random sampling, so we can implement it with low-speed analog-to-digital converters. And it needs to be a sublinear recovery algorithm, so we can compute very large FFTs in real time. So how does this sparse Fourier transform works? So say this is your input time signal, and let's say this spectrum is extremely sparse. It just has 3 peaks. So the way it works at a very high level is in 2 steps: bucketize and estimate. In the first step, we're going to divide this spectrum into buckets such that the value we get for each bucket is the sum of frequency coefficients within that bucket. If we can do that, most of the buckets are going to be empty, so we can immediately ignore all the frequencies in them. We don't need to go and run more computations on those. And for the buckets that are not empty, we need to estimate. So out of all the frequency coefficients that mapped into that bucket, which one is the large one? So how do we bucketize and estimate cheaply?
So just to understand.
Yes.
So you have a very wide band spectrum, but you can build low-pass filters or band-pass filters potentially, right?
So this is one way to bucketize, is like by bandpass, where that's not what we're going to use actually in a second. Because to build such a thing, you would require kind of to sample at the highest sampling rate. So we cannot bucketize this way. It's just for illustration, it's easier to see this form of bucketization. So how are we going to really bucketize? So if you know signal processing, you know that if you subsample a signal in time below the Nyquist sampling rate, what you get in frequency is aliasing of the spectrum. What does this mean? Let's take an example. Let's say this is your time signal, and this is its frequency spectrum. If you subsample this, take every other sample, and then take an FFT of half the size, the spectrum is going to fold on itself. So basically, every 2 frequencies are going to sum up together. And really, this is a form of bucketization, where frequencies, every 2, sum up in one bucket. And it turns out this is a very easy and cheap way to bucketize. All you have to do, you can subsample using a low-speed ADC, and then take a much smaller FFT. So now let's take a toy example. So let's say this is the spectrum, and it has only 4 frequencies. And we subsample it. We take every other sample, so it's going to alias. And then they're going to sum up together in buckets. Most of the buckets will be empty, and we can ignore them. And there are 2 other types of buckets, ones that have collisions, and ones that have just a single isolated frequency that map to that bucket. So let us, for now, focus on the isolated frequencies. We can find their value from the value of the bucket, but what we don't know is out of the frequencies that mapped into that bucket, which one is the red one. So to do that, to figure out, we're going to leverage a property of Fourier transform, which says that a shift in time creates a phase rotation in frequency. What does that mean? If we cannot repeat the same process with a shifted version of the signal by a time shift of tau, the phase of that signal is going to change by 2 pi f tau, where f is the frequency that we're looking for. So we know tau because we can pick it. We can measure the change in phase, and from it estimate the frequency f. Good. But what about buckets that have collision? The phase is not going to depend on either. So to solve these, what we're going to do is we're going to bucketize again, but we're going to use a property of coprime subsampling. So we're going to subsample again at a rate that's coprime with the subsampling rate we used the first time. And this coprime property is going to ensure that if two frequencies collide in the first bucketization, they're not going to collide in the second. So if we take this example and we bucketize again with this coprime subsampling rate, we are guaranteed that the green and blue are not going to collide again in the second one. And now all we have to do is iterate between the two. We estimate the frequencies that are isolated, and then we go and subtract them. Once we subtract them, more frequencies will get isolated. We can estimate them, subtract them, and we can keep going back and forth until we've found all the frequencies.
Question.
Yes?
So how do you know that a frequency is isolated and is not?
Yes. So basically, if a frequency is isolated, between the bucketization and the shifted bucketization, the magnitude of that frequencies remain constant, right? Only the phase change.
So you do a matching.
Yes. Whereas if there's a collision, both magnitude and phase change. So what can we show about this? So we can show for the exactly sparse case, but only when the frequencies are randomly chosen, we can show that the algorithm will take order k samples and will run in k log n computations. And for the approximately k-sparse case, the algorithm will take k log n samples and will run in k log squared n computation. And it's good to note here that basically Pawar and Kannan here at Berkeley independently reached the same result around the same time. They just used the coding theory approach to solve the problem. Yes?
Just wondering, is the bad case when you of having multiple things in the same bucket corresponding to having them equally spaced in the frequency domain?
Is it bad thing?
Yeah, is that the, like, where does the random break down?
So basically, the randomness, yeah. So basically he's saying, why do we need it to be random? So we need it to be random is because our algorithm is not randomizing things. So that's why we can prove an average case analysis of the problem. We cannot prove it in the worst case. Because basically we are limited by how many coprime subsamplings we can do, right? So other versions of the algorithm where we can take random samples, we can have worst case guarantees, so we don't care where the k-sparse, what's the distribution they come from. But in this case, because we're limited by how many coprime samplings we can get, right, we have to have an assumption on the sparsity.
Right, so I guess my question is, there is some pattern to the sparsity, right? Like there is some, the way the FCC says there
yeah, so that's exactly true. So what he's saying is, yeah, but in practice it's not random, right? And indeed you can use that if you feed that as a prior, that you know that if a frequency is there, then there's a band that FCC set that you can know that the entire band is there. And of course you can use that in practice to really improve the algorithm. So you cluster frequencies together, based on what FCC allocated. Okay? So now with that, we can actually build a gigahertz receiver because we subsample the data uniformly, so we can use a bunch of low-speed ADCs, and we have a fast algorithm which won't compute a lot of power. And so we went ahead and we used software-defined radios to build a receiver that can capture almost a gigahertz of spectrum, right, in real time, using a bunch of low-speed ADCs with an accumulated digital bandwidth of 150 megahertz, so 6 times less. And basically what we've shown is that roughly up to 5%, it works really well. So I'm not going to go into the empirical results, so we can move on, but they're in the paper. So at this stage, someone should stop me and say, look, The entire goal of what you're doing is to make the spectrum get used efficiently, right? And if the spectrum is being used efficiently, then it's not going to be sparse. So we kind of went back and defeated the entire purpose. So what are we going to do? What if the spectrum is not sparse? Is there anything we can do, or are we just doomed? We have to use like high-speed ADCs. And it turns out we're not. And because if the spectrum is not sparse, we can take the signal and actually make it sparse. Let me tell you what we mean by that. So let us say this is a non-sparse spectrum that is being used efficiently. What we're going to do before sampling or anything, we're going to pass it through a hardware filter that looks like a comb. So basically, it kind of subsamples these frequencies. So this is a filter in hardware. And once it subsamples these frequencies, you get a very sparse spectrum. And you can pass this sparse spectrum to a sparse Fourier transform algorithm, so you can now subsample at very low rates and solve the problem. Now, of course, you're not recovering the entire signal, but what you're recovering is the occupancy. So you're recovering the occupancy of each of these bands. And that's the goal. So we now no longer can recover the entire signal, so you cannot decode, for example. But what you can do is sense which bands are being used and which are not. And actually, building such a thing turned out to be very, very hard. And only until recently, like a colleague of mine used MEMS acoustic resonators to build these highly tunable comb filters. And we showed that actually now you can build such things and then pass it through, and then the problem becomes actually simple, even when the spectrum is not sparse.
Sorry, what's the tuning that you need for the
Basically, we tune how far these are apart, right? And basically how much loss you get. Yes?
And that's a function of how finely you need to
Sample. Yeah. So basically, this will be set, mostly will be set by how probably the FCC allocates the bands, right? So if the bands are very small, if I divide my bandwidth into 1 megahertz chunks, then probably I need 1 megahertz. If I divide it into 10 megahertz chunks, then probably I need one every 10 megahertz. Okay. So with this, with the sparse Fourier transform, we've shown how we can capture and sense gigahertz of spectrum in real time. Now let's move to the second problem, which is millimeter wave networks.
Sorry, just to
Yes.
conclude, you do know the occupancy, and you will say use the low occupied frequency. As you said, you don't know, you can't recover the signal in that frequency, so you will have a collision. Are
you cannot recover, so you're not transmitting yet, right? So you're sensing to discover which are occupied. Now the truth of the matter is that, like, let's say the algorithm decided that this band is occupied, you can actually go and sense it exactly with like a narrow band filter, right? And detect, make sure that your the result is correct. And the other thing is that, I don't want to go into details, but there's some confidence metrics that when you recover some frequencies, how well you're confident that this is correct, that you can extract from the algorithm.
But your original goal was to find spectrum to use.
Yes.
So after you discover that this is an underused part of the spectrum, and you decide to use it, you still have to recover that signal so you can cancel.
So basically, once you discover it's unused, right, you can kind of just, so basically this is going to be a separate circuit for just sensing, that you do it continuously, right? And then you'll have your traditional like low tens of megahertz kind of band that you can use. So basically the only difference now is you add basically part of the circuit that's dedicated for sensing and discovering the bands, and then you tune your center frequency to what it is.
So how does the receiver then tune into you, because you're sort of dynamic?
Yes, so this is a good question. Is like I'm sensing, how does my receiver know where I am, right? So there needs to be some coordination, right? And like if we basically both should be sensing, and there seems to be.
You don't assume that there exists some sort of pilot channel.
Yeah. So basically, for the purposes of this, we're not looking at the protocol of how we coordinate to make sure we're on the same channel. But you're right. Okay. So let's move to millimeter wave. And basically, if we look at the wireless spectrum between 0 and 100 gigahertz, for the last X number of years, we've actually been operating here, below 6 gigahertz. And that's why the spectrum ran out. And there's plenty of spectrum, tons of gigahertz of spectrum that is not being used. And recently, the FCC realized that and started to open more and more spectrum, some of it for licensed use, for cellular, some of it for unlicensed use. And right now, you have almost more than 14 gigahertz, around 60, of unlicensed spectrum that anyone can use for free. And this is more than everything we've ever dreamed of. There's lots of applications. So these are called millimeter wave bands. And there are lots of applications. The main one is for 5G cellular network access and backhaul. But there are other applications in virtual reality, wireless data centers, and connected vehicles.
Can I ask a very naive question?
Yeah.
So what is the problem with this higher frequency signals? Is that you
Yeah.
need more energy to send them, or they reach us?
They reach, exactly. So nothing is for free, right? We get tons of bandwidth, but the signal attenuates really fast. So the range is very limited. And what you need to do to compensate for that is today you have one antenna on your receiver or transmitter. But with millimeter wave, you have to have an antenna array, and that allows you to focus the direction of communication. So you focus all your power in one direction to compensate for the loss. And the good news is because the frequency is so high, the wavelength is so small that we can build very large antenna arrays. So we can put hundreds to thousands of antenna elements on the back of your phone and basically extend the range very wide and get very narrow beam. The problem with this is that it really changes the way wireless networks operate. So today, all wireless networks, cellular and Wi-Fi, are what we call broadcast. So when you transmit, the signal goes in all directions. And the truth of the matter, that's a blessing, because no matter where you are, you're going to receive the signal. And even if you move, you're still going to receive the signal. But if you go to millimeter wave and you're using these very narrow beams, basically, unless the beams are aligned, sometimes you can't even know that there is an access point. So basically, communication at very high data rates is only going to be possible when the two beams are aligned. And even worse, if you just move a bit, the connection drops and you have to realign again. So how can we align? Well, the naive way is to do an exhaustive search. So if you have n directions that you can beam in, right? You can try for every direction at the access point, or at the client, you try all possible directions at the access point. And so the problem with this is that it takes order n squared measurements. And here a measurement is actually you send a data packet, small one, and you measure the value of the channel. And so this is, even for small arrays, it's prohibitively expensive. Like, no one even thinks of implementing this. So when the people who do the standards started, so they decided that this is way too much, so we're going to do something simpler. So the standard for millimeter wave is something called 822.11ad. And the idea they came up with is we're going to do it in two stages. The first stage, the access point is going to have a very narrow beam, and the client is going to switch to what they call a quasi-omnidirectional beam. So it's almost omnidirectional. And then the AP is going to scan, and the client will then discover the best direction from the AP. And then in the second stage, we're going to reverse the roles. The AP has a quasi-omnidirectional, and the client is very directional. And then the client is going to scan. And then we're going to pick the best direction from both sides. And the issue with this is that we're still scanning. So for n direction, we still need to send n packets, right? And what people have shown is this is still too slow. And if you want to accommodate mobility, you need to be able to do it much faster. Yes?
This reminds me of the same thing we were talking slightly earlier. It's for saying I want to know what frequency you're transmitting in.
Yeah.
And I will do that with a sideband. Here, I need to know where you are.
Yeah. So I need to know the direction of your signal, because sometimes in kind of non-line of sight, the direct path is blocked. So you need to kind of use a reflection to communicate.
Right.
Yeah. But basically, yeah, because it's very easy to get blocked because it's narrow and it attenuates quickly. But basically, you're right, and it's kind of the same problem as we want to discover the direction the signal can come from, right? And so the question we're going to ask is, how can we find the right alignment in sublinear number of measurements, and without having to go and scan and try all possible directions? So before I tell you, I need to tell you a bit how the millimeter wave radio kind of creates these beams. So what happens is there's an antenna array, right? And then each antenna is connected to what we call a phase shifter. So it just modifies the phase of the signal on each antenna before they sum up. And by setting these phases, you kind of create this directional beam. And by changing them, you can steer it in any direction. Now, if we look at the antenna array theory, the math tells us that the signal on each antenna is actually nothing but an inverse Fourier transform matrix multiplied by the vector x, where x represents the directions where the signal can come from. So if x is a vector that represents the different directions, f is the inverse Fourier matrix, then the signal on each antenna is just f times x. And then what you can control is how you set these phase shifter values. So every phase shifter adds a phase, so it's of the form e to the j phi. So what we're doing here, we're taking the signals, multiplying them with e to the j phi, summing them. This is one measurement. So we can represent it as a vector A of the phase shifts multiplied by fx. And if we take a lot of measurements, we get a matrix A that's mixing fx. And again, there's been a lot of measurement work in millimeter wave. And all this work, both indoors and outdoors, led to the conclusion that actually the vector x is very sparse. And the reason is that the signal takes only few paths between transmitter and receivers. Because at millimeter wave frequencies, there's much less scattering. So it's mostly reflections. So there's only few paths from any transmitter to a receiver, mostly 3, 4 maximum, even indoors. So basically, the vector x is sparse. And now we don't have much constraints. We can set A the way we like. And so we can use compressive sensing or sparse Fourier transform to solve the problem.
Can I ask another naive question?
There's no naive questions.
So how do I know the signal I'm receiving is the one that I'm...
So basically, there is some packet that has a header, right, that tells you the access point ID, right, IP address or MAC address, right, so that you can tell that this is an access point. So basically, it's all in the higher layer protocols on how to kind of sense this, solve this addressing problem.
Are these antenna arrays already off-the-shelf standards compliant, or do you have to just introduce them?
So basically, there are a lot of off-the-shelf, right? There is even access points. The only issue that I see is that the hardware design is pretty bad. So you don't get very narrow beams, and there's lots of like what we call side lobe leakages that kind of really makes the beam not very narrow. But basically, in people are it's still in academia stage, but people have built very large arrays, like people at UCSD build a 256 array that has very narrow beams. But the stuff you find like on commercial devices has very low number of antennas, and basically it has very wide beams, yes, still.
And the power consumption is comparable to?
No, it's more. Basically, because you have very large bandwidth, you sample at very high data rates. And so basically, that's why mostly you have one receiver. You cannot put a receiver on every antenna, for example. It's way too much. Okay, so basically, this is sparse. This is a standard sparse recovery problem, but turns out it's not as simple. So it turns out there's a catch here, and the catch is there's something in RF called carrier frequency offset. And for the purposes of this talk, you don't really need to know what that is. But what you need to know is actually it creates kind of a phase that corrupts the phase of the signal that we're measuring. And this phase changes very quickly with time. So every time we send a packet, it adds a random phase to it. And it's very hard to track and estimate. So basically, what ends up happening is that the phase of these measurements end up being useless. And what we need to do is take the magnitude to eliminate this component. And so what this becomes is a well-known problem called sparse phase retrieval problem. So how are we going to solve it? Let me give you a very high level what's the intuition. So let's say this is the access point, and it's at 60 degrees relative to the client. What we're going to do is construct what we like to call a multi-armed beams. And what this means is like a beam that have directions, arms in different directions. If you use that to capture the signal, then you can know you'll get some signal, and you can know that potentially the directions are 0, 60, 90, or 120. And if you repeat this a few times with different multi-armed beams, now you know it's 40, 60, 100, or 150. So you can combine this to figure out that, oh, it's 60 degrees. That's the right direction. Yes?
So in the three-dimensional case?
So you have a 2D array, and you have a 3D beamforming. So you basically have what we call azimuth and elevation planes. So you can steer it this way, right?
You get the flexibility for the lobes.
Yeah, yeah. Of course, it depends how you build your hardware. But assuming you put a phase shifter on every antenna, then you can steer in 3D. OK. So 2 questions we need to answer. How the hell do we generate these multi-armed beams? And what is the best choice of these multi-armed beams? So let's first start with the first one. If we look at this problem, if we look at the vector A, to create a beam that is traditional and very directional, we can actually pick A as to be any row of the Fourier matrix. So if you pick A to be any row, this is how the beam will look like. You change the row, you get a different beam. What we want is something like this. So what we're going to do is divide the vector A into multiple segments, and then choose these different segments from different rows of the Fourier matrix. And by changing which rows, we can randomize which directions the beam has. OK, so this is the first. The second question is, how do we pick these beams, and what's the best choice? And here we have to be a bit careful, because with the reflections, especially if you have metal reflectors, and you use a beam, the signal can combine destructively to attenuate itself. So you can miss some of the signals if you're not careful. So what you need to do to solve this problem is basically have some randomization. And so what we need to do is pick these multi-armed beams to create sorts of random hash functions. So where if we kind of look at the different directions, each set of directions map to one bin. And so if we use random hashing, then all we have to do is use a voting-based process to figure out which directions the signal comes from. Now, of course, there's a lot of more details, because Actually, the beams are not that discrete, and you cannot separate them that easily, but I'll leave that for the paper. So what can we show? What we can show is if you have n...
Just quick question.
Yeah.
In everything you're telling us now is the AP that has all this multi-arm beaming, and so the client is just...
Yeah, so basically, everything I've discussed assumes that the client is kind of omnidirectional. There is an extension that it's not part of the talk, but basically you'll incur a k² here instead of k if you were to do it from both sides at the same time, right?
I mean, it's not a bad thing to have the client be just simple.
Yeah, so there is issues with these kind of creating omnidirectional beams at millimeter wave. It's actually very hard. Then they look very crappy, sorry for the word, right? So that's why it's better to avoid them, but it actually makes the protocol simpler for sure. Yeah. So what we can show is that you can do it in k log n, where k is the number of paths between transmitter and receiver, and n is the total number of directions. So what we did to test this, we built a millimeter wave radio with phased arrays. And of course, I'm not going to go in the interest of time because we're out. I'm not going to go into the details. But what we can show is you can really quickly align the beam in less than 1 millisecond, even through simulations. If you go to 256 antenna array, so you can possibly get 256 directions, you can get something that's 100 times faster than what the standard does today, and almost 10,000 times faster than exhaustive search. So, to conclude, so I talked about 2 applications. Of course, there's way more applications of sparse Fourier transform, but I focused on spectrum sensing and showed how to capture gigahertz of spectrum in real time, and millimeter wave networks, and show how to align the beam so that you can have a continuous communication really fast. So thank you very much, and I will take questions.
We've already asked a bunch of questions, but maybe time for 1 or 2 questions.
It's not directly related, but it seems like you could be able to use this for multicast as well. So in your car example, if one car wants to talk to multiple,
you can create the beam to send it to multiple devices. Indeed, yeah.
is it still easy to detect the directions? So you want to detect.
So basically, the process is that. So the way the protocols are set, right, is that there is a learning stage. It's called beam training, like where you can quickly discover the directions to different devices you want to communicate with, and then there's a data transmission phase, right? And the goal is to kind of minimize the overhead of the learning stage as much as possible, and do it quickly so that as the guy moves, you continue. It doesn't change. The beam doesn't change. Now the good news is that because the data rates are so high, the packets can be small, so we can actually send quite a few before the beam changes.
If you could localize your position accurately.
Yeah, so in line of sight, it kind of helps a lot because then I know. In non-line of sight, it doesn't because I still need to know the paths.
Okay, so let's thank Haitham and
Thank you.
Sophia for their talks. Thank you.